Okay, what I'm going to do is go through some of the homework problems that we did last week, because a couple of you wanted some explanation on a vodcast, so I'll go over the numbers that you see there on the screen. I'm going to do this all in one shot, so I don't think it should take too long, but it might take between about 10 and 15 minutes. Okay, let's get started with number 34, and I'll just read the question real quick. You've got a reaction written there, A decomposing into B. And it says that at a particular temperature, the initial concentration is 2 times 10 to the negative second molar. And time concentration versus time data was collected, and a plot of the natural log versus time resulted in a straight line with a slope of negative 2.97 times 10 to the negative second. And then there are 3 questions here. So the first one says, determine the rate law. So since we said that it's the natural log versus time, we know that that's going to be a first order reaction as long as the k value, or I should say the slope of the line, is negative. So we know it's going to be first order, so our rate law will be R is equal to k, concentration of A, and that would be raised to the first power, which you know we don't have to write the ones there. The integrated rate law, which we talked about, you know, takes a number of different forms. So I'll just write it in the form natural log final concentration is equal to negative k times t plus natural log of initial concentration. So just pay attention that you remember that the k value there is negative. That's going to be the slope of our line, and that's what tells us that that line is going to be, or I should say the slope of that line is going to be negative. Remember, this form of the equation takes the, or this equation takes the form y is equal to negative mx plus b. We're going to solve for k there, so we don't really need to solve for k because, again, the slope of our line is equal to k. So that is going to be equal to negative 2.97 times 10 to the negative second. Part B then says calculate the half-life, and you remember T sub 1/2 stands for half-life. So since it's a first order equation, we know that the half-life equation is 0.693 over K. So we're simply going to substitute our value for K, and when we calculate, we should get approximately 23.3 minutes. Just want to pay attention to your units. In K up here, the unit is given in minutes, so we'll use minutes for our time unit. Part C says time is required for the concentration of A to decrease to, there it is, 2.5 times 10 to the negative third molar. So we can use our integrated form. Now we know the final concentration, so again, and you can do this a number of ways. I'm going to use natural log final over initial is equal to negative kt. So I'm going to plug in my final concentration there, my initial concentration there. Now remember, you want to do this fraction first. In other words, take 2.5 times 10 to the negative third divided by 2 times 10 to the negative second. Get your value for that, and then take the natural log of it. We're going to plug in our value for k into there, and then we will solve for t. And we should get time is equal to approximately 70 minutes. Again, just notice, do the division there first, and remember, k for a first order process is negative unless you write it in a different form, which is possible. Alright, let's move on to number 36, and number 36 is basically the same type of question, but the question says in this case it's the inverse of the concentration versus time, which gives a negative slope. So we're plotting our inverse of concentration versus time, and we get our, actually I'm sorry, you get a positive slope, not a negative slope. So that's going to indicate a second order process. So when we go to write our rate law, we are going to write it R is equal to K, concentration of A, raised to the second order. The integrated form of that will then take the form that we talked about. And again, you can write this a number of ways, but I will write it 1 over final concentration is equal to positive K times T plus 1 over initial concentration. Again, that initial could be a 0 and then nothing written there. There's a number of ways to write it. As usual, I write I for initial and F for final as my subscript. And then we're going to determine the rate constant, and again, that is equal to the slope of the line. So our slope here is equal to the rate constant. Notice the units, liters per moles times seconds, and that's for a second order process. Remember, a first order process is going to be inverse seconds or inverse time. Second order will be liters per moles times second. Third order would be liters squared over moles squared times seconds, etc. Alright, part C, it says calculate the half-life. So again, we are going to plug in to our half-life equation, and you just want to remember that the half-life equation for a second order process is 1 over K times the initial concentration. The important part here to remember is that in a second order process, the half-life is dependent upon the original concentration of the compound. First order process, it's not. And remember, radioactive decay always undergoes a first order process, but this isn't radioactive decay here that we're talking about. Okay, in part C, you're going to calculate the amount of time again. Until what? Time for the concentration to be 7 times 10 to the negative fourth. So instead of rewriting this, I will take that concentration, put it in for final, take my initial, put it in for initial, my value for K in for K, and I'm going to solve for T, and I will get T is equal to 2.98 times 10 to the fourth, and that's going to be in seconds. Again, pay attention to the units for K. The time unit here is seconds. Okay, let's move on, and we will talk about number 41. Now in 41, this is where you've plotted, or I should say you've collected concentrations for A, and you made 3 plots, and in the book your 3 plots are concentration versus time, natural log of concentration versus time, and then inverse of concentration versus time. So we have our data, we've calculated what the natural logs of those concentrations would be, what the inverses of those concentrations would be, and we've made 3 separate graphs. The concentration graph basically looks like that. The natural log graph looks like that. And the inverse graph looks like that. In case my artwork isn't up to your standards, that one is supposed to be the straight line. So we know that the inverse relationship tells us that this order, or this reaction, is second order. If this one were the straight line, it would be first order, and if this one were the straight line, it would be 0 order. But it's this one, so that tells us that it's a second order reaction. I believe that's all we're doing in letter A. Let's take a look at number 42. So what we're going to do with 42 is we're going to take our plot from number 41, and we're going to answer the following questions. What is the concentration of A after 9 seconds? So since this is a first order process, since this is a second order process, actually let's go back here. Okay, from your data here, if you look at the book, you will see, let Let me get my pen back. If you look at the book, what you're supposed to be able to identify is where that line would cross the x-axis. And if you do that, what you're going to see is that it should cross at about the value of 10. So since it's the inverse of the concentration, 1 over 10 is equal to 0.1. So our initial concentration of the A should be approximately 0.1. From this line, you should also be able to calculate the slope. And if you pick 2 points on the graph, and I just picked 60 minus 20 for the rise, and the run 5 minus 1, you should get a slope equal to approximately 10. So when you go back to our problem over here, you should have a slope equal to 10, our initial concentration equal to 0.1, and since it's a second order process, we're going to write our integrated rate equation. Alright, so if we're looking for one of the concentrations, it would be better to use the form, let's write it this way. 1 over final concentration is equal to negative kT plus 1 over initial concentration. So we're going to solve for 1 over x is equal to negative 10, our time is 9, plus 1 over our initial concentration, which we said was 9. So we should get a value for our final concentration, approximately 0.01 molar. So you can work through the math there and make sure your answer agrees with mine. Okay, since this is a second order process, we're going to find the first 3 half-lives. So the first one, T1 half, is equal to 1 over our K value, which is 10. And then we're going to multiply by the initial concentration, which we said was 0.1, and we're going to get a value of 1 second. Our second half-life, we're going to have 1 over 10. Now our new initial concentration is going to be half of what the original was, so it would be 0.5. So that should be 2 seconds. And then our third half-life should take 1 over 10.25, which will give us 4 seconds. And again, you can work through the math there. Alright, let's do the last one here and finish this up. Number 46 says what? It says the radioactive isotope P32 decays by first order kinetics, has a half-life of 14.3 days, and we want to know how long it will take to use up 95% of our material. This is a very classic radioactive decay or half-life problem. Right, since it's first order, we know it's going to be natural log final over initial equal to negative kT. So what we want to do is solve for T, and we want to know what our initial concentration is and our final concentration. So what we can do to do that, we need to figure out what K is. So to do that, since we know what the half-life is, we can say our half-life time is equal to 0.693 over our K value. So that's our half-life equation for first order. So we would find that K is equal to 4.85 times 10 to the negative second days, and that'll be inverse days actually. So now that we know what K is, we need to know what our initial and final concentrations are. Well, it doesn't really matter what they are because we know 95% of it will decay. So if our initial is 100, our final would be 5. In other words, 95% of it decayed, so there's 5% left as the final concentration. So we can set this up negative, and so I don't use scientific notation and Jamie doesn't get mad. I will write this as 0.0485 and I will solve for T. And I'll find that T is approximately 62 days. So that is it. That's a pretty typical first order kinetics half-life problem. And again, remember, all radioactive decay undergoes a first order process. Okay, I think that pretty much sums it up. If you have any questions, you're certainly welcome to email or stop by my room before the exam tomorrow. I will I will edit this quick and get it posted. Thanks. See you tomorrow.